Here are the solutions for the extension problems number 12 through 16. Here there's a graphing problem. You're supposed to graph the parent function first and then graph the main function, drawing the asymptote, showing the domain and the range. First of all, you might see this in this format instead of with this star here. You might see multiplication with parentheses. Okay. Basically, here the parent function can be identified by this base. Okay. And so if I was to write the parent function by itself, I would write y equals 2 to the x. So let's graph the parent function first and then show how to graph this function using transformations. So 2 to the x is, let's see, I'm going to put a few values of x here. And each one of these I'm going to plug into 2 to the x. So 2 to the negative 1, 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8, because 2 times 2 times 2 is 8. Okay? So I'm going to now graph each of the points for the parent function. So it's going to be negative 1, comma 1/2. 0, comma 1, 1, comma 2, and 2, comma 4, and 3, comma 8 is off the screen. And then I kind of join those with a curve. It looks kind of like that. And it's going to approach the asymptote, which for a parent function for exponentials is a line that is exactly on top of the x-axis. Okay, that is the asymptote for the parent function. Actually, what they want you to graph here is the asymptote for the function itself. So let's graph the function itself. Now, you might take the table and then graph the function itself by plugging in numbers. But since you already have the parent function graphed, why don't we use the transformations to graph it? So first of all, we have 3 transformations here. The first transformation that we should look at is the vertical stretch. The vertical stretch happens to be a negative stretch, which means not only are we going to stretch this in the opposite direction, we're going to stretch it by a factor of 2 upside down. Okay. So, for example, if we start out with positive 1 here, then this point here is going to be stretched in the negative direction by a factor of 2. This 0.5 here, positive 0.5, is going to turn into negative 1. Positive 2 is going to turn into negative 4, and then the next point is going to be totally off the screen, right? So here we got an image of a upside down function, okay? And the only thing we've done so far is we've done the multiplication by negative 2, the A transformation, okay? And then the next transformation we're going to do is we're going to look at C and D. So in this case, the C value is going to be negative 2. Because C is actually minus C, and here we have plus 2, so it's a minus a negative 2. So our C value is negative 2. Our D value is negative 3. And so we're going to do a transformation, a translation, a horizontal translation 2 to the left, and a vertical translation 3 down. So we're going to take each one of the points here, and we are going to go 2 to the left, and 3 down. So for example, this point here is going to go here. This point here is going to go here. This point here is going to go off the screen down here. And then the asymptote, instead of being on the x-axis here, it's going to go 3 down. The asymptote, of course, is not affected by the horizontal translation does not affect the asymptote. Only the vertical translation affects the asymptote. So there we've inverted it, and we inverted it, stretched it by a factor of 2. We've moved it left by 2, and we've moved it down by 3. Finally, let's take a look at the domain and the range. The domain for exponential functions is always all real numbers. We write it like that. X is an element of all real numbers. And the range here is going to be for all values of y. No, not all values of y. It's only going to be for the values of y that are below 2. So I'm going to put y is less than negative 2. Okay? All right. Next one here. Natural log of 5x plus natural log of 2x equals 8. Natural log pretty much works the same as log base 10 in terms of log rules. So the fact that this is a natural log, the only thing it changes is when we do the snail, we are going to use a base of e. Okay? So I'll show you that in a bit. But first of all, we're just going to use the log rules to combine a sum of logs. A sum of logs is equal to a product of the insides together, right? So if I have the log of a plus the log of b, this is equal to the log of a times b. So here I'm going to take 5x, I'm going to take 2x, and then I'm going to multiply them together inside the natural log function. Okay? And I haven't done anything to change the value of the left side, so the 8 remains there. Now I'm going to do the snail. Oh, wait, first let me simplify this. So 5x times 2x, of course, equal to 10x squared. Okay? Now I can do the snail. Remember, whenever you do the snail, you should have the log on the left and the number on the right, which I do. Just to make things a little bit easier, I'm going to change the notation here. Instead of natural log, I'm going to write log base e. Remember, e is a number that is 2.71. And then I'm going to do the snail. So there's the snail's head, and then it goes around here, and it goes around there. So basically the way snail works is I'm going to change log to an exponential expression. So I'm going to take the base e, and then I'm going to take it to the power of 8, and that's going to equal 10x squared. So I'm going to rewrite it here. Base e to the power of 8 is equal to 10x squared. So I have just rewritten my log expression into an exponential expression. And now I can just solve for x, because x is no longer inside the log. I can just do regular algebra. I can divide both sides by 10, and I will get e to the 8 divided by 10 equals x squared. And now I can just take the square root of both sides, and then I'll get x equals the square root of e to the 8 over 10, which is equal to the square root of the top, which is square root of e to the 8 would be e to the 4th, and then the square root of the bottom, which is square root of 10, is just square root of 10. Okay, so there's my answer for that one. Number 14. Log base 7 of this minus log base 7 of this equals 1. Okay, remember that if you have a difference of logs, log of a minus the log of b, that's the same as log of a divided by b. So let me do that. So I'm going to do log base 7 of 2x minus 3 divided by x plus 2 equals 1. And now I'm going to do the snail to convert it into an exponential expression. I'm going to say 7 to the power of 1 is equal to this expression here. Okay, so 7 to the 1 is equal to 2x minus 3 divided by x plus 2. And now I'm going to manipulate algebraically this expression to solve for x. This is probably slightly difficult algebra for you because you haven't reviewed it in a while. But basically I'm going to cross multiply. And then I end up with 7x plus 14 equals 2x minus 3. And then I'm going to subtract 2x from both sides, and then I get 5x. And then I subtract 14 from both sides, I get negative 17 on the right. And then I can divide both sides by 5, and I get x equals negative 17 fifths. Okay. Finally, number 15. Here I have a compound interest problem, so I want to use the formula future value equals present value times 1 plus the rate divided by the compounding number of compounding periods to the kn power, where n is the number of years. Okay, so it says invested $500 and the rate is 6.5%, which is 0.065 in decimal, and divided by 12 because it says monthly. And then the number of years is 7. Okay, find the value of their investment after 7 years. So here I just need to simplify this and do the calculation. So it's going to be 500 times, and then I can do the rest of this in the calculator. So I would have a 500 times 1 plus, and then I'm going to make a fractional expression with 0.065 on top and 12 on the bottom. So I go to math, number, and then n divided by d. This is really useful so that you don't need to worry so much about parentheses. I can input it exactly like it appears in the problem, and then I don't need to worry if I need to put extra parentheses around the fraction. And then I need to put an exponent of 12 times 7. Okay, and the answer is 787.12 cents. Okay, and IB, you should always put finance numbers up to the 2 decimal places, like in cents. Okay. And let me get this out of the way. Okay, now let's go to the last number here. Depreciation on a car can be determined by the formula V equals C to the 1 minus R to the T, where V is the value of the car after T years, C is the original cost, and R is the rate of depreciation. If a car's cost when it's new is $15,000, the rate of depreciation is 30%, and the value of the car is now $3,000. How old is the car to the nearest tenth of the year? Okay, so V is going to be, let me write the whole expression here. So V is the value of the car later, C is the original cost, R is the rate of depreciation. So the rate of depreciation is 30%. In a decimal, we put 0.30. The T we don't know. The C is 15,000 because that's how much it cost when it was new. And then the value of the car now is 3,000, so we put that here. Now we're going to isolate the T, and you're like, how do I do that? Because it's in the exponent. Well, this is the reason why we have logs, okay? So we're going to divide both sides by 15,000, so we end up with 3,000 divided by 15,000 equals 1 minus 0.3 is equal to 0.7, and then to the T power, okay? And so the left side, 3,000 divided by 15,000 becomes 0.2, and now it's a pretty simple expression, but how do we find this on the calculator? Okay, so the way we do this is we rewrite it as a log, and remember that if you have 0.7t on the left and 0.2 on the right, you can use the snail to rewrite this as a log. So the way you rewrite it is you take the first value, which is log of 0.7 of 0.2 is equal to t. And we've just solved the problem. The answer to this is log of 0.7, log base 0.7 of 0.2. Okay, that's what we want. We wanted the answer to t. Now, of course, the calculator doesn't do base 0.7. But you can rewrite this using the log rules, and you can rewrite this as log of 0.2 divided by log of 0.7, right? There's a log rule that says log base c of a is equal to the log of a divided by the log of c using any base. Okay, you can use base 10 or you can use base e, which are the ones that the calculator can do. Okay, so I'm going to show you how to do this on the calculator. You can use either type of natural log or log. So first I'm going to do regular log base 10. So I'm going to do log base 10 of 0.2 divided by log base 10 of 0.7. And that gives me a result of 4.51. I'm going to write that down first. And then I'm going to show you how natural log is going to give you the same answer. Natural log of 0.2 divided by natural log of 0.7 also gives me 4.512. Okay, and now I'm going to translate this into number nearest tenth of a year. So we're going to round this to 4.5 years. Okay, and that's it. That's the last one. Yeah, the rest of it's in the other video.